All right, so this set of notes, I'm going to go back over 4.3, all right, the derivative of the exponential function base e and the derivative of the natural log function that we're using in the 4.4 applications. All right, so first the exponential function base e. And so the simplest expression of the exponential function is some number a times the e raised to our x variable, all right? And so a is just a number. The e is that natural number e, right? That's the base, and it is e raised to the x value, so it's e raised to our variable. And so when we take the derivative of that, all right, when I take the change in y over change in x, f prime of x, what makes the exponential base e function, the natural base, unique is that it's a function where its derivative is itself. All right, so when I take the derivative of this function, it's exactly the same as the original function. It grows at a rate proportional to its size, and so this is its size, and so that's how fast it's growing. It's growing by its size. And so it is simply just the original expression. So if I start with a 10e to the x, right, its derivative is 10e to the x. Right, if I have a negative 200e to the x, its derivative is negative 100e to the x. Its derivative is just itself. And so, coincidentally, its second derivative is also itself. Right? If I take the second derivative of g, it's also negative. And so they keep going on. The third derivative would be negative 100e to the x. The fourth derivative would be negative 100e to the x. And so when it's just the e to the x, right, some number times e to the x, its derivative is itself. Right? Again, it's unique to the exponential base e. It works for the base e. If I have something other than base e, this doesn't work. All right, so we just look at the derivative for base e because it's the simplest case. All right, you can always convert to it. Again, all of our applications will already be set up that way. All right, where things get a little more interesting is when we have the chain rule. All right, so the chain rule and the exponential, which means my function, I'm going to write it capital H of x, is some exponential expression. So a is a number, e raised to, but instead of x, up inside there, up in the exponent, is a function of x. All right, so the outside would be the e expression. The inside would be that g of x, and so that's why we have a chain rule that's involved. And so remember, the chain rule is, it's the derivative of the outside. Well, the outside is the e part, so the derivative of the e is itself. So the first thing I write down is the original expression. All right, a times e to whatever that g of x function is. But I'm not done yet. Remember the chain rule, derivative of the outside times the derivative of the inside. And so separately, I'm going to multiply by the derivative of just that inside function, just this g of x, whatever it is, and it's separate. All right, so I've got my original expression here, separated by a multiplication is then the derivative of whatever the expression was up in my exponential. And it could be just a simple expression, e to the 2x, right? So we'll look at an example of that. Suppose we started out with the function 10e raised to the 2x. Well, the 2x is the g of x part, right? 10e to the 2x. And so when I take the derivative of that, there's something other than x up there. There's a 2 times x, and so I have to use my chain rule. All right, so the derivative, first thing you do is write down the original expression. So 10e to the 2x gets written down. But I'm not done yet, and this is the part you have to remember. That's just the outside. I've got to remember times the derivative of the inside. So I've got to take the derivative of 2 of x and multiply by it. Well, the derivative of 2x is just 2, and so it's going to just get multiplied by 2. So I get 10e to the 2x times 2. Simplify that. I can take my 2 times my 10 to get 20e to the 2x, and there's the derivative of that function. All right, so doing another example where maybe it's a little more complex. All right, so I've got my g of x function, which is negative 3 times e raised to that quadratic, right, x squared plus 5x minus 2. And so when I take the derivative of g, the first thing you do is write the original expression down without changing a thing. So negative 3e to the x squared plus 5x minus 2, but I'm not done yet. That's the outside. Separately, separated by a multiplication, I take the derivative of just the exponent, the quadratic inside. And so I'm going to take the derivative using our old rules. Derivative of x squared is 2x to the first. The derivative of 5x is just 5. The derivative of the negative 2 zeroes out. And there's the derivative of that expression. It's the original times the derivative of the exponent. All right, and let's just do another example. Let's not do g. Let's do p of x. All right, 5e to the negative x. All right, now this one seems simple, but since there's the negative up there, it does require the chain rule. The first thing you do write down when you're taking the derivative of p is 5e to the negative x, but you're not done yet. You still have to take the derivative of the inside. Take that derivative of the negative x. Derivative of negative x is negative 1, and then I'll multiply the negative 1 times the 5. Negative 5e to the negative x is its derivative. All right, so that's the derivative of the exponential. Base e. Again, only works for base e. If it's a different base, it would require different rules. And we're only going to do base e in this class. All right, now a reminder of the natural log function. All right, the natural log derivative. All right, so remember the natural log is the function ln of x. If x is positive, right, I can only plug positive numbers in. So the same thing's true about its derivative. X has to be positive. All right, so again, I can only try on your calculator, try to plug a negative number in, you can't. All right, so when I take the derivative of this, and this is just something you're going to have to memorize. The derivative of the natural log is 1 over x if my x values are positive. So again, it's 1 over x if x is greater than 0. Sometimes we get around the if x is greater than 0 by saying absolute value of x. But I'm just going to leave it like that. The derivative of the natural log is 1 over x. Derivative of natural log is 1 over x. And so if I have a function that's 3 times the natural log of x, well, its derivative, the 3 is just a constant multiplier, it's going to come along, times the derivative of natural log, well, the derivative of natural log is 1 over x, and so it simplifies to 3 over x. All right, again, so natural 3 times the derivative of natural log is 3 times 1 over x, which simplifies to 3 over x. All right, same thing with the natural log. Its derivative really isn't too bad, right? If I look at it, it's just simply, and what's nice about it is when I take the derivative of natural log, it no longer has a natural log, right? Derivative of natural log is 1 over x. There's no natural log in the expression. And that's kind of nice. Now, where things get a little more interesting is, again, if we've used the chain rule. All right, so the chain rule and the natural log. All right, so suppose I have a function that's a natural log, but instead of the natural log of just a variable, like x, there's an expression in there, a function in there. So it's the natural log of a function, right? And again, it could be a simple function as simple as 2 times x, but that's a function of x. And so it's the natural log of g of x, right? So this requires my chain rule because I've got 2 functions. This is the natural log on the outside and the g of x on the inside. And so when you take the derivative of this, right, the natural log part's the same. The derivative of natural log is 1 over the function inside. And so 1 over whatever's inside, right? And that's true for the previous case, right? When it's just x, it's 1 over what's inside, 1 over x. But with a chain rule, you're not done yet. That's just the natural log part. You've got to remember times the derivative of what's inside. And so times the derivative of the inside function, the g of x. And then we usually simplify it. And so in the denominator, it's g of x, what was inside. And in the numerator, it's the derivative of whatever's inside. Because eventually we're going to do antiderivatives. And so we're going to recognize when we see this type of ratio that the original function was a natural log. Right? If I have a function in the denominator, its derivative is in the numerator. All right? The only function that gives us that is our natural log. All right? And so we'll work backwards from that. All right, so some practice problems. All right, so suppose I have the natural log of x cubed plus 3. Right? So it's the natural log of, so natural log is the outside function, the cube is the inside function, and so it follows this rule. When I take the derivative of this h of x, it's 1 over what's inside without changing it, so it's 1 over x cubed plus 3, but I'm not done yet. It's now the derivative of the inside, which is 3 times x to the second, and then we usually rewrite it as a single fraction. So 3 times x squared over x cubed plus 3, and nothing simplifies. You can't cancel the x's, don't do it. All right, that is the derivative of h of x. You're done. All right, 3, so this is the function inside, and this is its derivative, right? So in the denominator is the function, and the numerator is the derivative of that function. All right, so let's do another example. All right, so if I have 10 times the natural log of 5 minus x squared. All right, so take the derivative of that. 10 comes along, so 10 times the derivative of the natural log, which is 1 over what's inside. So 1 over the 5 minus x squared times the derivative of the inside, which is going to give me a negative 2x, right? The derivative of the 5 zeros out. I pull out my 2 with my negative. That's where the negative 2 comes from. And then 1 degree less is 1. And then we do usually rewrite that as a single fraction. So up top, I'm going to multiply the 10 and the negative 2x to get negative 20x. And the denominator stays the same, right? Nothing simplifies. That's the derivative of f of x. All right, let's do another one. All right, so I've got 25 times the natural log of x to the 5th plus 6x minus e to the x. And so the derivative, 25 is just a constant multiplier, it's going to come along. The derivative of the natural log is the chain rule, 1 over what's inside. All right, as is, so exactly the same expression inside, x to the 5th plus 6x minus the e term. But I'm not done yet. That's just the log part. Separately, and separated by multiplication, I take the derivative of the inside. So the derivative of the inside, power rule, 5x to the 4th plus 6 minus e to the x, right? Because the derivative of e to the x is e to the x. And then we usually write it as a single fraction. All right, up top I'm just going to write 25 times that, 5x to the 4th plus 6 minus the e to the x, all over x to the 5th. 6x minus e to the x, and nothing reduces. All right, don't cancel anything out, leave it exactly. All right, so I'm going to do a couple of examples where we'll mix it with our product rule and our chain rule. All right, so that was the logarithm. All right, so do an example with the product rule. All right, so e to the 2x times the natural log of x. All right, so this is the product rule. Right, with the exponential rule with the chain, and then just the plain old logarithmic rule. The e term is the first function, natural log is the second. All right, so the product rule is the first, which I am just going to write down e to the 2x, times the derivative of the second, which is 1 over x, plus the second, times the derivative of the first, which is going to require my chain rule. All right, so the derivative of e is itself, so write down the 2e to the x, but again, remember, you're not done yet because of the 2x. You've got to remember derivative of 2x, so times 2. All right, and there's the derivative. Now, I will clean this up a little bit. I'm going to factor. All right, I've got an e in both. I can pull out to the front, so I'm going to factor the e to the 2x out. When I do, all right, e to the 2x is gone, so in the first term, I'm left with 1 over x, and the second term, the e's gone, but I still have the 2 ln of x. And again, it's a minor thing, but it just cleans it up a little bit and makes it a little easier to work with. All right, so my next example, I'm going to do the quotient rule. so I've got 2e to the x divided by the natural log of 5x. So quotient rule. All right, my low function's the log, my high function's the e. It is the log of 5x, so I'll have to use my chain rule. All right, so remember, the quotient rule is the low function, low, so the natural log of 5x, times the derivative of the high, which is just 2e to the x, right? It's the simple case, so the derivative of 2e to the x is 2e to the x, minus the high, 2e to the x, times the derivative of the low, so this is going to require my chain rule, because I've got a 5x, so it's 1 over the function inside, so 1 over the 5x, but I'm not done yet, times the derivative of the function inside, so times 5. Alright, so low, derivative of the high, minus the high, derivative of the low, all over the low function squared. And again, you need to put parentheses, it's that entire log function squared. Now again, that's its derivative. I am going to clean it up a little bit. Alright, so first of all, I can factor out a 2e to the x, so I can pull that out front. Alright, factor it out, and then what's left over, and I'm still going to leave the denominator the same. Alright, so again, 2e to the x is gone, so in the first term I'm just left with the natural log of 5x. Minus, in the second term, this is gone, and I'm actually also going to simplify here. This 5 and this 5 reduced to 1, and so in that second term, I'm just left with 1 over x. And and again, it's simplified. You cannot reduce anything. This natural log does not cancel with that natural log. You can't do that. It doesn't work that way. And so this is as simplified as it goes. And so if you're having trouble with this, go look at the extra practice worksheet in the folders. And it works through some examples where it goes through some different cases. All right, that's sort of a quick and dirty reminder of the logarithm and exponential rules that we learned before break.